In a previous lecture on material and heat balance in roasting, I have shown all the problems that we are going to take up. In that lecture, I could solve problem 1, 2 and 7, though all the problems and the data I have given in an earlier lecture. So, here just for the sake of so that you know, I am just repeating those problems which are already there in my previous lecture. So, the problem 3 refers to the roasting of zinc concentrate, the compositions are given, the conditions are given and the roast product which can form under the given conditions of roasting are given, and you have to find out rate of blowing air, excess air, analysis of flue gases, and I have also written here perform heat balance of the roasting per ton of concentrate. That means, you have to calculate for 1 ton of concentrate what are the roast product and so on. Problem 4th is for the roasting of copper concentrate. Here also the same thing, compositions are given and the roast product formation, what can form, how, what is the Cu2s composition, what is the Cu and so on. The problem illustrates everything over there. So, again you have to calculate here the percentage sulfur in the roast product, weight of roast product, volume of air, and also I have given that you require to calculate heat balance of the process also. Now, problem 5th, again it is a roasting of zinc concentrate, but here you are using coal, coal composition is given. Here both the say the products of combustion as well as the roasting gases which are evolved, both are mixing and they are going together. They are little bit different in the statement of the problem, and the solution may not be similar to the earlier, but well there is a little bit difference and you have to catch that particular point to solve that problem. Problem 6 is about the galena concentrates, and that should be not very difficult, and again here the roasting of galena, and here again furnace is fired with coal and you have to calculate weight of roasted ore, volume of furnace gases, weight of coal used. Now, you must have noted that in all the problems on roasting, what you require say roasted product, volume of gases, volume of air, excess air, and heat balance if it is required to be done. I mean the whole objective of heat balance is to know what is the excess heat or deficit heat or whatever. 7th problem I already done. So, just I am going over here. So, here I am just projecting once again the data which are there in my previous lecture slide. I have illustrated the data and you can note down from there, and these are the further data for the problems on material and heat balance in roasting. And the about the answers, well I had already given in my earlier lecture, but here once again I will like to give you the answer, but my appeal as usual, please do not see the answer before you solve the problem completely, only see the answer after you have solved the problem. So, now I will proceed to solve the problem number 3. So, let us take problem number 3. I will just draw a block diagram because I am habitual whenever I solve the problems on material balance, I try to write what is given and what is required in the form of a block diagram, so that I know what is given and what is being formed, how it is formed and so on. This is the way I do it. However, you can do your own way, you do not need to do the way I do it. So, this is what the material balance box is, the roasting unit. So, here I have zinc sulphide, lead sulphide, FeS2 and inerts. Zinc sulphide is given 76%, lead sulphide is 7%, FeS2 is 7% and inerts are 10%. You do not bother about inerts, that means they are not taking part in the reaction and as such. So, you do not need to bother. About the roast product, the problem says the roast product consists of ZnO, PbO and Fe3O4. The roast product will also be accompanied by gases, and it is said that there is SO2 which is 7%, and SO3 is 2.5%. That is what is given in the problem. Additionally, it is given that zinc sulphide converts to ZNO, PbS to PbO and FeS2 to Fe3O4, and sulphur is converting into SO2 and SO3, mind you, not only in SO2. So, here the problem is slightly different. If you attempt to calculate volume of air by writing down the stoichiometric equations, the ZNS plus 1.5 O2 is equal to ZNO plus SO2 or SO3, you will not be able to write that equation, because here the SO2 and SO3 both are forming on roasting of zinc sulphide. So, in that way there is a new type of problem. You have to think it over how you will calculate volume of air. Earlier we have calculated by assuming the stoichiometric amount of reaction, because all sulphur was transferring to SO2, but here you cannot do it, because sulphur is transferring to SO2 and SO3, and unless you know the mole proportions, you cannot write any balanced chemical equation. So, you cannot calculate oxygen. So, a different approach has to be evolved, has to be thought, has to be innovated in order to solve this particular problem. So, let us see. First of all, basis as usual 1 ton concentrate or 1000 kg concentrate. So, first of all, you have to calculate, for example, rate of blowing of air. Well, rate of blowing of air is not that easy that straight away you can calculate. You have to know how much amount of air you are blowing. You cannot write down the balanced chemical equation. So, you do not know what is the amount of oxygen. So, you have to first of all catch up how much amount of flue gas is forming. How will you do it? You have to perform sulphur balance, because all the sulphur which is there, it is now transferring into the flue gas. So, that is the clue now. So, by doing that sulphur balance, you can calculate the amount of flue gas. So, as such I am performing sulphur balance. I am performing sulphur balance. Now, let us take, say, let x kg mole is the flue gas. Having said this thing, now I have to find out the sulphur input should be equal to sulphur output. Now, the key to this problem, the straight away I am doing the balance, because I am noting in the roast product there is no sulphur. So, straight away I can do sulphur in the feed, sulphur in the gases. So, sulphur in the feed I can convert these percentage into kg and kg to kg mole. Now, for zinc I use the atomic weight 65, for lead 207, and for sulphur 32, for iron it is 56. So, straight away what I can do, 760 is the weight of ZNS. So, 760 divided by 97, that will be the kg moles of ZNS, and hence the same kg mole of sulphur also. So, that way you can do that sulphur balance. So, what I am writing straight away 7.835 plus 0.292 plus 1.167, that is equal to 0.07 plus 0.025 into x. Now, mind you, here in the zinc concentrate given is FeS2, not FeS. So, that point is to be noted, it is not FeS, it is FeS2. So, accordingly this is the sulphur balance. Now, I can straight away solve this equation. So, the flue gas that will be coming 97.84 kg moles. Now, I know now the amount of flue gas. However, you can also like to do it, you can also take sulphur balance, let x kg or x meter cube flue gas. Accordingly, you can also calculate. The choice is yours, the way you want to proceed. So, now let us go a step further. So, now we know that SO2 that will be equal to 6.849 kg moles. Now, we can find out the amount of flue gases. SO3 that is equal to 2.446. Now, here a little conceptual thinking is also required to solve this problem. Now, if you see this particular problem, you can note that the roasting gases or the gases evolved during roasting will be comprising of SO2, SO3, nitrogen and oxygen. So, I mean that thing you have to evolve after reading my conceptual lectures on roasting, that once you know which gases will be present, then you can proceed to solve this problem. So, in this case you have nitrogen and nitrogen plus oxygen. Now, why I am writing oxygen also here? Because I do not know whether the roasting is carried out at stoichiometric amount or some excess air is used. This problem does not say anywhere. There is no mention that the stoichiometric amount of air is used. So, keeping that thing in mind, I have to be cautious and I have to see that the roasting gases will be comprising of nitrogen as well as oxygen. So, this N2 plus A2, that will be equal to, and there is nothing, and there no other gas is there, no fuel is used, no CO2, no CO and no other gas except these 4 gases, they constitute the flue gas. So, N2 plus O2, that will be equal to 97.84, that is the amount of flue gas, minus 6.849 plus 2.446. So, that makes 88.545, mind you, all in kg moles. What to do now? We have to know nitrogen and oxygen. Now, here we have to make use of that the kg mole of air, 1 kg mole oxygen, 3.76 moles of nitrogen. So, let us say that, let us consider, let y kg mole is nitrogen in flue gas, Then how much will be oxygen? Oxygen will be equal to 88.545 minus y, that will be moles of oxygen. Now, what air contains? Air contains, what air will contain? Y kg mole nitrogen, y kg mole nitrogen plus 0.21 y upon 0.79 moles of oxygen. So, we have to also, after this we have to find out the analysis of Roche product. So, the Roche product as per the statement of the problem consists of ZNO, that will be equal to 7.835 all in kg moles, PbO 0.293 and Fe3O4, that is equal to 0.194. Now, I can do the oxygen balance, that is the oxygen from air and oxygen utilized in the system. So, if I do that oxygen balance, I am writing down 0.21 y upon 79, that will be equal to 0.79, that will be equal to 7.835 upon 2 plus 0.293 upon 2 plus 0.194 into 2 plus 6.849 plus 2.446 into 1.5 plus 88.545 minus y. Now, this is for ZNS to ZNO, this is for PBS to PBO, this is for Fe3O4, this is for SO2, this is for SO3 and this is the excess oxygen. So, if I solve, then the value of y that will be equal to 81.78 kg moles. So, now I know O2 in flue gas, that will be equal to 6.768. So, that is the O2 in. Now, once I know the O2 in flue gas, now I can calculate rate of blowing of air, that is what it is asked, rate of blowing of air, that will be 81.78 upon 0.79 into 22.4 into 100 upon 24 into 3600, assuming that 24 hours the operation continues. So, that will be equal to 2.68 meter cube per second, that is the answer. So, the next thing said excess air, you know now how to calculate, that is the excess oxygen divided by the stoichiometric amount, that already I have calculated, and you can calculate that comes to 45.2%, that is the excess air. Now, you have to calculate the analysis of flue gases. Now, it is straightforward. So, the flue gas will have SO2, it will have SO3, it will have N2, it will have O2. So, about the moles you can write down, all the percentages are given. So, I am straight away writing SO2 is 7% as it is given, SO3 will be 2.5% and N2 will be 83.6% and O2 will be 6.9%. So, the total moles of flue gas, that will be equal to 97.843 kg moles. Now, if you want to know in volume, a little bit exercise you have to do it, you have to multiply 97.843 into 22.4, that will be in meter cube. This is the say for the flue gas. Now, the problem further says you have to perform the heat balance. Now, in performing the heat balance, you have to know heat input and heat output. Now, heat input, because the reactants, say ore and ore concentrate plus air, they all enter at 298 Kelvin. So, there will be no sensible heat which is entering along with the reactant, because they are all at 298 Kelvin. Now, the heat input will be the heat of reaction at 298 Kelvin, right. That is the only heat input. Heat output, so heat input will be, the data are given, heat input will be, say heat of reaction, all these data are given. So, I will omit all this calculation. So, heat input, that will be equal to 1436,756 kilocalorie. You can calculate all that, you have to multiply from the data which are given. Say for example, Zn plus half O2 ZnO, heat of formation of ZnO is given, 7.835 is the ZnO which is produced. So, ZnO, that is 7.835 into 83,500. If you see those data sheet, you will find all that you have to multiply in it's very simple, and you will get this particular figure. Now, heat output, say heat output, the heat output one will be for roast product. Now, the roast product leaving at 1100 degree Kelvin, as the problem says, the roast product they leave at 1100 Kelvin and gases also leave at 1100 Kelvin. So, for the simplicity, I have given the heat content of the roast product at 1100, that is I had already given H 1100 minus H 298 for ZnO, for PbO and for Fe3O4. So, all that what you have to do, you have to multiply the H 1100 minus H298 value with the respective moles, you sum total it, you will get the heat taken away by the roast product. So, I am leaving this exercise to be done by you. So, heat output by roast product, that is heat output by roast product or if you wish I can just write down some of the values. So, that will be 7.835 into 9500 plus 0.293 into 10,800 plus 0.194 into 40,350. Now, you have to sum total. So, heat output will be equal to 85424.8 kilocalorie. Now, similarly, you have to calculate heat output by gases. Or heat carried away by gases, whichever way you want to understand. You know all the gases SO2, SO3, N2 and oxygen. So, I will write down now again for your quick calculation the heat content say H 1100 minus H298 for SO2, SO3, N2 and O2 they are given say kilocalorie per kg mole. So, straight away you have to multiply, but my sincere advice at this stage of your learning would be you take the appropriate value of Cp. I already gave you the reference from which you can have the value. You develop the skill of integration and then use this particular value. That will be good for your future building. So, well, for the quick estimation I am writing here 6.849 into 9397 plus 2.446 into 13860, that is H 1100 minus H 298 for SO3 plus 81.78 into 5916. 5916 is the H 1100 minus H 298 for nitrogen and plus 6.77 into 6208. So, total heat carried away by the gases, that will be 624,100. Now, here you will be noticing, and that is very important thing in case of roasting, that alone nitrogen is carrying away a large chunk of heat. Now, if you just want to see the percentage, it will come around 60 to 70% of the heat carried away by the gases, it is carried away by the nitrogen. So, there is a scope of heat recovery from the gases. Remember, these gases are living at 1100 Kelvin. So, higher is the temperature, according to second law of thermodynamics, higher is the quality of heat, because the quality of heat is directly proportional to the temperature at which the gases are discharged. So, when the temperature is very high, then the quality of heat is very good, is very high, and accordingly one should think also in the direction of energy or heat recovery from these gases. You see that around 70 to 80% of the heat is taken by the roasting, and remember this particular aspect is the key feature of development in roasting technologies. For example, use of oxygen enriched air, that is what I thought I will illustrate. Now, if we do the heat balance, just to illustrate what I have right now said. So, heat input that will be the heat of reaction and nothing else, heat of reaction, and that is equal to 1436,756 in kilocalorie. That means, in percent, say 100% of the heat which is required for the roasting is supplied by the heat of reaction, that is what the 100% means. Now, sensible heat, the sensible heat of reactant, that is equal to 0, because they are all at 298 Kelvin. Now, in the heat output, so let me put the green thing. Heat output first is the sensible heat in roast product, that is equal to 85424.8 kilocalorie. Now, in gases, say SO2, I am combining both plus SO3, they both takes only 98,262 kilocalorie of heat. Now, alone nitrogen, now you can see nitrogen is taking 483,810 kilocalorie of heat. It is very large chunk. Similarly, oxygen is say 420, not 420, I mean 42,028 kilocalorie of the heat. So, now because there will be some heat losses, so I have to add heat losses, and normally say what we do, in the absence of anything we take 10% of heat input. So, if you do that, then the losses will be 143,675.6. So, total heat out, that will be 853,200.4. So, roasting of zinc concentrate in this particular problem, it is accompanied by a surplus heat, and this surplus heat is 583,555.6, that constitutes around 40.62% of heat input. I mean, this is a calculation based on the only the heat output terms, gases, roast product and losses, could be other losses also, but what can be said, that roasting process could be an autogenous process. A large amount of heat is being generated, and if precaution is not taken, then temperature may rise in the reactor. So, one is to be careful about the temperature which can be raised by the excess amount of heat. It was just an illustration. So, this is all about problem number 3. Now, let me take quickly problem number 4. Now, problem number 4 is very similar to problem number 3. Here also you have to do, well, heat balance head is easy, but what is first required is the material balance, because you cannot get rid of the material balance, because unless you do material balance you cannot do heat balance, right. So, first you have to do the material balance, and you have to find out what is said weight of roasted product, volume of gases, then composition of gases, and then you can perform the heat balance of the process. So, now in this particular problem, this is again a little different problem. In order to do material balance, you have to use first of all your intelligence to do the entire material balance. Now, this particular problem says that furnace gases analyze 12% oxygen and nothing else is given. Of course, some other conditions of roasting is given. So, here you have to think intuitively how to calculate the volume of gases and amount of air, because again you cannot write down the stoichiometric reaction, because it has been 12% oxygen. Anyway, so if you do that, for example, I will go quickly because similar problem I have solved. So, let us take now say 1000 kg concentrate. If we take 1000 kg concentrate, then we can calculate the amount of CuFeS2 which is there, Cu2s, FeS2, SiO2 and moisture. Now, one can calculate the moles, say 1.793, 0.438, 2.833, 3.167 and moisture is 3.889. They are all in kg moles, and I think I repeatedly give, but my duty to give you again. Copper I am using 64, sulfur I am using 32, iron is 56, silicon is 28, and well O is 16, I mean nothing to write from here. So, H2O becomes 18. So, now weight of roasted product we have to calculate. Now, the condition, all iron is oxidized to Fe2O3 and 50% copper oxidizes to CuO and rest to Cu2S. So, you have to first of all do all these calculation. So, first let us find out the copper in ore concentrate. You will first find out copper in ore concentrate, that you can find out, divide into 50%. So, then you can calculate amount of CuO, and amount of Cu2S. Now, both these amounts they are coming 106.76 kg and this amount is also 106.76 kg. So, you have to calculate now the Fe2O3. So, you calculate iron in the concentrate, iron in concentrate, then you calculate Fe2O3 from that. So, Fe2O3 would be 370.08 kg. This you can calculate, and of course, all SiO2 will enter into the roast product. So, SiO2 will be 190 kg. So, you can calculate now. So, the total roast product that will be equal to 773.6 kg is the total roast product. So, you can find out now percentage sulfur in the roast product and percentage sulfur in the ore concentrate, that will be say percent sulfur in the roast product, that will be equal to 2.76%. And if you express a sulfur in roast product upon sulfur in ore concentrate into 100, this will be around 6.7%. So, now we have to calculate volume of air and excess air. Now, let us see how we will calculate. So, total sulfur charged that is equal to 310 kg. Now, mind you, this is the way I am doing it, but I thought that this way I could do it. I am 100% confident that you might have thought some other way of doing this particular problem. I will suggest or request that please follow your way and let it be innovative solution. Do not follow what I say. So, total sulfur charge is 310 kg. Now, all sulfur is converted to SO2, all sulfur is converted to SO2 except that which is in roast product, am I right? Which is in roast product, because we calculated roast product, it has certain amount of sulfur. So, that will not be going into gases. So, that means, now since we know the sulfur which is in the roast product, so I can calculate now sulfur which is going to SO2, that will be equal to 310 minus 20.8, that will be equal to 289.2 kg, and this will be equal to 9.04 kg moles. So, it will be 9.04 kg moles. Now, H2O we know it is 3.89 kg moles. That straight away you can write down very easily, straight away it goes now. Now, here you can calculate theoretical amount of oxygen, because the problem does not say that sulfur is converted to SO2 and SO3 like, I mean, unlikely, say in the problem 3 it was said that SO2 and SO3, so it was difficult for you to write down the stoichiometric reaction. But since the problem is silent on this, so you can take it for granted that sulfur is converted according to stoichiometry of the reaction and SO2. So, that makes your life little easy. So, we have to calculate now theoretical oxygen, and theoretical oxygen, that will be S to SO2, Cu to CuO and Fe to Fe2O3. This is where you will be requiring oxygen. So, you can calculate the oxygen S to SO2, that will be 9.04 plus Cu to CO 1.3345 upon 2 plus 2.313 into 1.5. Mind you, they are all in kg moles, all in kg moles. So, if I sum total, that becomes equal to 13.20 kg moles. Now, what I do now? What will I do with this oxygen? Now, this oxygen I have to calculate, or I had calculated, keeping in mind that at least I will be able to know the theoretical nitrogen that should have gone into the flue gas. Theoretical oxygen will not go in the flue gas, because it is available in the form of roasting product or gases. But theoretical nitrogen definitely will be available. The problem says 12% excess oxygen. So, that means there is the excess oxygen, but then at least I am able to know what is the amount of nitrogen that is theoretically is there, and it will go to gases. So, that way I calculate, which I can calculate now. So, theoretical nitrogen, that will be equal to 3.76 of this. So, that will be 49.632 kg moles. Now, what should I do further now? I know now theoretical nitrogen that must have gone into the gases, but still that is not the end of the solution, because you have to know the total amount of nitrogen, because excess oxygen is there. So, you have to do now, let Z kg mole is the flue gas, Z kg mole is flue gas. So, 0.12 Z kg mole of oxygen in flue gas. You agree with me? Now, what to do? I know now the excess oxygen in the flue gas, that is 0.12 Z. So, accordingly excess nitrogen, how much it will be? Excess nitrogen in flue gas, that will be equal to 0.12 Z into 3.76, that will be equal to 0.451 Z. Now, I know the total amount of flue gas in terms of Z, plus some values are known to me. So, now I can write down the flue gas. Now, you note from here how important it is, first of all, to know the concept of roasting, how important it is to understand how the roasting is carried out, how the air is being utilized, how the excess air is being used, where the theoretical air goes, where the actual amount of air it is available in the flue gas, that is only in the form of oxygen. Theoretical oxygen will not be available to you in the gases. So, this is where the concept of roasting is required in order to solve this particular problem. Now, the flue gas will contain what? SO2, H2O, then excess oxygen and nitrogen. Now, nitrogen I can divide in two parts according to my problem, one corresponding to the theoretical and another corresponding to excess oxygen, there will be excess nitrogen also. So, it is very easy now, I can write down now 9.04 plus 3.89 plus 49.632 plus 0.12 Z plus 0.451 Z, that is equal to Z. Now, this is SO2, this is H2O, this is theoretical nitrogen, this is excess oxygen, and this is nitrogen corresponding to excess nitrogen, corresponding to excess oxygen, that is all. Now, you can solve this equation. So, Z will be equal to 145.83 kg moles. Well, of course, that you can convert now to meter cube. This will be 592 meter cube, 180 m and 273 Kelvin. Now, everything can be calculated. Now, you can calculate volume of air. Now, you can calculate volume of air, and that volume of air, that will come 3272.68. Now, in all the problems you might have noted that amount of air or volume of air and volume of flue gas is in the ratio of 1:1, that is what you must have noted. So, here lies the self checking of the problem. While solving the problem, if suppose you get the flue gas amount is 50% of the air, you must think that you have committed a mistake somewhere. You are seeing in almost all the problem it always 1:1 ratio, around 1 to 0.98 or 1:1 ratio. So, that is also a clue, and that is also the thing which should be perceived while solving the problem. These are the certain things that you should develop when you solve an unknown problem and when you have committed a mistake. So, if you keep these ratios in mind and then you solve the problem, if all of a sudden you get the ratio 0.5, you must think that you did a mistake. So, that is also one of the objective of solving the problem, to see that you develop skill to solve the problem for the future. So, that is an important thing. So, now I can do now excess air. I will quickly go through, because these things I have already illustrated, that will be around 132.576%. You do not need to go 3 decimal, but well I have written. So, the composition now I can write down SO2, H2O, nitrogen and oxygen. So, the percentage are 6.3%, 2.7%, 79% and 12%. So, this is how this analysis goes. Now, a quick glance at the heat balance. Now, here heat balance, now it can be done at two approaches. Say one approach is that you write roasting reaction, you write all roasting reaction and determine heat of reaction, that is one way, and determine heat of reaction. Determine heat of reaction. Say for example, Cu2S to Cuo, write down that equation, find out the heat of, that is one way. Another way is that we know the roast product, we know the roast product. We get heat input from various heat of information of individual reactions. For example, we know the roast product Cuo, say roast product comprised of Cuo, Fe2O3, Cu2S and SO2. So, Cuo forming Cu plus half O2, Fe2O3 will be 2 Fe plus 1.5 O2 and so on. So, I can just calculate the heat of formation and multiply, I will get, you can follow this way or this way. I am going following the roast product because the values are given. So, I can calculate now heat liberated, heat liberated, I will be straight away multiplying the moles with the values of the heat of formation of the product. So, if I do that, then heat liberated will become 1164,446 kilocalorie. That is the thing. Now, heat output one heat output will be as usual by flue gases, and the another heat output will be Roche product. Now, here the chalcopyrite concentrate consists of CuFeS2. So, one has to have some heat of decomposition of CuFeS2, that also we have to consider. So, this heat, so that is equal to 39,975 kilocalorie per kg mole of CuFeS2. Now, with this I can now write down heat output by flue gases, say heat out by flue gases, that will be equal to then heat out by Roche product, then third will be heat of decomposition of chalcopyrite, heat of decomposition of CuFeS2, and then heat losses. So, heat losses I am doing 10% of heat input. So, all these values, well, you can write down. So, say heat out by flue gases, that will be 7066 to 2.7, they are in kilocalorie. By Roche product it will be 92243.1. By the heat of decomposition of CuFeS2, that will be 71675, and 10% heat losses, that will be 116444. So, if you sum total and subtract it from the heat input, then you will find that surplus heat in this particular situation is 177461, that is in kilocalorie. So, that is what the advantage, or that is what the idea that you get by performing heat balance. You know beforehand that well, so much amount of excessive heat is available, what should be done? If not proper care has been taken, then the temperature during the roasting will rise, and sufficient steps can be taken to rectify the rise in temperature vis-a-vis cooling medium or whatever you want to do it. So, problem 5 and 6, please solve yourself, the answers are given.